Hello to everyone, I'm Tomislav Shuminovski, Assistant Professor at the Faculty of Electrical Engineering and Information Technology in Skopje, Macedonia, and I will present the video material named Virtual Networks SDN and NFV. I would like to emphasize that this video material is supported from Erasmus Plus K203 project named Innovative Teaching Approaches in Development of Software Designed Instrumentation and its Application in Real-Time Systems. So the presentation is organized as following. In the beginning, we have some introduction about network virtualization, and after that we are starting with SDN, SDN architecture, SDN objectives, SDN capabilities, SDN open flow, and SDN security as a first part of this presentation. And the second part is more details about NFV architecture, benefits, and relationship between those two significant parts from network virtualization. And in the end, we will finish our presentation with conclusion. In the beginning, I would like to say that the network virtualization is defined as a process of combining hardware and software, network resources and network functionalities in one single software-based administrative entity named virtual network. Actually, the network virtualization or virtual networks is composed from those two things, SDN from one side and plus NFV. The trend beyond network virtualization goes also to software defined instrumentation and is giving innovative approaches, new types of application, and many other advantages. What's the big picture? The big picture of network virtualization is presented here. So from one side we have software defined networks, which creates network abstractions to enable faster innovation and faster management and control of the entire core network. On the other side we have open innovation, which creates competitive supply of innovative applications by the third parties, and in the bottom we have network function virtualization, which reduces capex, opex, and give more space and power in less power consumption. NFV also aligns closely with SDN objectives to use commonly services and switches, and of course SDN provide different level of control and perspective in today's and future networks. What is the basic definition for the SDN? The basic definition of software-defined networking is that it is emerging network architecture which decouples the network control from the forwarding function or the data where data flows, enabling the network control to become directly programmable and the underlying infrastructure to be abstracted from applications and network services, which means that it centralizes command and control in the network and separates the control plane from the data plane. That's the very important issue in those SDN networks. Of course, we have management plane, which is separate from control and data plane, and manage those two planes. Although SDN is a relatively new area, it has attracted very much attention, not only from researchers and academia, but also from business, regulatory, and industry part. Here we have the, the, uh, the those three different planes and how they interact with well-known OC model. Uh, Basically, where data flows is only physical layer, and the control layer is up to transport layer, and above is management or application layer. How we send that on the network and how to manage the network. More closely said, we have this SDN architecture separated on those three layers. Down we have network infrastructure, core network, routers, switches, base stations, access points, and etc. etc. On the control layer we have SDN controllers, and above we have different applications and as cloud SDN, etc. Also, we have here presented a concept given by ITU, how they look on SDN in the recommendation Y3300. Which is very important here is that we have well-defined programmable interfaces between control and data planes, between this control and data planes, and of course the bottleneck is SDN controllers. So the main brain of those SDN lies here in the controllers. Above we have SDN applications, and below the network, as we know, where the packets are flowing. All applications running on controller actually manage and control the underlying platform. Also, SDN recalculates the control of network resources to a dedicated network elements, namely these controllers. And here we give a presentation of the of more detailed overview of the SDN functional architecture given by ITUT 3302, and as we can see, we have multi-layer management orchestrations on those three layers, and here we have separated the SDN application layer in management support orchestration, SDN application. Also we have application support control layer, service and resource abstractions here on the control layer, and as we see, we have different interfaces communicating one with each other. Basically said, we have also external relationship management with other non-SDN networks, and all those functions are named multi-layer management function. For more detail, you can see this recommendation given from ITUT. What are the objectives of SDN? The objectives are to realize faster network business cycles, to reduce which means that SDN must reduce the response time from business requests to network providers. Also accelerate innovations as business, also the technical innovations, not only the business, which give more flexible networks, easy for to be administrated, and to organize those operation and maintenance of entire network, and accelerate adaptation to customer demands, or in other words, SDN facilitates the accommodation of customers' connectivity requirements by means of dynamic negotiation of network service characteristics and the resource control on the other side. Furthermore, we are continuing with also two very important objectives, that SDN improves resource availability and usage efficiency, uh, which means that SDN must to improve network resource availability and efficiency, in particular when combining with network virtualization due to introduction of high level of automation and overall service delivery and operation procedures. Also, on the other side, we have customization of network resources, including service-aware networking, which is novel concept in the future and nowadays networks. What this mean? It means that SDN allows network customization for the network services, which have different requirements for different services and also different sets of quality of service parameters and provisioning. Uh, Also, here we are including dynamic enforcement and sets of policies uh, and quality of service performance that the customers want to have. Uh, Here we give one unified SDN overview uh, from the access point to data centers and clouds, how and where the virtualization happens. Virtualization happens, as we say, separate and above from the network infrastructure which goes below. Of course, we should have uh, specialized or novel routers and switches which can be programmable and can be controlled from SDN controller. Later we will mention what is more specific details about the SDN controllers. Also, here we can see all those players in this SDN unified overview from end to end. What are the high level capabilities in SDN? First of all, we have programmability, which is behavior of the network resources that can be customized by SDN application through a standardized programming interface for network control and management functionality. Previously, we haven't such a commodity and a way of programming the entire network. So the user of the interface may be network provider, service provider, customers, business sector, including end user. All of them can give extra code and program those switches and nodes uh, implemented in SDN, and of course to implement novel SDN applications. Furthermore, we have resource abstractions, as we mentioned previously. It's a property and behavior of underlying network resources that can be appropriately abstracted and understood, orchestrated and controlled and managed by the third party or the controllers which goes above those network infrastructure, which can those controllers can install a program, can give control on the underlying network, and these models provide detailed abstracted view of physical or virtualized network resources. Here we have the function capabilities separated in this slide. How the service creation goes. We can have intelligence steering, dynamic offloading, subscriber personalization, and using of those services. Above on the application layer, control layer, we can have more network automation for the telcos and cloud interaction between VPNs, scaling and load sharing, and of course additional services which are not offered previously. And all of this we have cost and efficiency saving by servicing abstraction, VPN automation, aware application aware techniques, and of course multi-layer transport. Furthermore, we will see more details about the SDN controller overview. Uh, the SDN controllers, as they are placed here, are on the network layer and are interacting with application, operating systems, and other stuffs above. And down we have the network infrastructure. Sure, we can be hybrid network, which includes legacy core networks and parts of the networks, as accesses, mobile, fixed, and etc. Other SDN networks, like we see SDN domain A, SDN domain B, and other virtual network. SDN controllers focus on network resource abstraction and path calculation, how to find the shortest path provided with higher quality of service provisioning from the source of the for that package to the destination. So actually this is the brain of the entire SDN networks. SDN controllers serve as a type of operating system for the network, if you say, or if you go in generalization, this is the SDN orchestration, which focus on end-to-end service and resource orchestration. It is the key to enable agile service across multi-domain, multi-layer, and multi-vendor network. So this is the key. One of the most famous protocol which enables SDN is OpenFlow, proposed by Stanford. What is very important is to emphasize that it's open source code to control universal SDN controllers and switches. So actually the network separation on the control and data plane management plane goes together with such an open virtual switches installation, in which we have OpenFlow protocol, and of course the one controller who interact with all those switches and routers in the core part of the network and communicate one with each other. And what we have OpenFlow, set of design specifications, messages, which we'll see later. Regarding testbeds of OpenFlow, there are many designs have been proposed and many versions, but only few survive the light of the day. In its current version, OpenFlow is not able to configure quality of service parameters and in a dynamic and on-demand manner. Only manually is provided. But in order to deal with quality of service problems in dynamic approaches, a framework called QoS Flow that enable quality of service management and quality of service provisioning in SDN networks is proposed by those authors in this paper. So we will focus a little on this specific OpenFlow protocol, which is extension of the standard OpenFlow controller. We see that cons of that basic standard OpenFlow. Okay, so you can see that this SDN OpenFlow controller is consisted of quality of service flow agents which communicate with JSON with the network administrator, and administrator communicate with this controller, and inside it has manager, monitor, and QoS database for clients. He uses API, QoS Flow API and NOx API, to communicate with data path, and switches and routers given here. And which is very important is using those specific APIs. We have user space and kernel space on the packet flow uh, space. Uh, the control architecture for QS optimization is given here, uh, where the controller has powerful capabilities to specify QS requirements, QS desirable parameters which should be achieved in order to have from end to end QS satisfyingly provisioning, and of course in the end of the day to have satisfied users. Uh, it can also directly control the flow table in order uh, to differentiate between different priorities of the traffic or different traffic flows and different users. The communication between the controller and the switches may be secured by some standards as using SSL. This is the open source network and open source network interference. Both we have security. Uh, in the SDN control architecture, the QS optimization, the following three extra features should exist. Uh, those are resource monitoring, uh, resource signaling, and resource reservation. What means resource monitoring? The forwarder should comprehensively monitor their available network resources and report periodically to the controller in order to stay alive and to dynamically have QS provisioning. The controller may pull the forwarder for such profile. Also, the signaling is very important because without signaling, the controller cannot communicate with the switches, and the certain actions cannot be taken by the controller, which is very important when we are changing QS parameters on the fly. And also, the signaling is responsible for updating the flow table. Uh, from time to time, it can happen to have reservation. Then the controller may command the forwarder to reserve certain resources for future QS needs. This reservation includes buffer size, which is specified by the controller, memory space, CPU calculate time, and any other resources. And we are going back on the OpenFlow model. Uh, in the OpenFlow model, is without quality of service provisioning. If you know that on the previous slide for the SDN QS control architecture, the forward layer has to implement the policy function in order to ensure that the clients obey the service level agreements where the QS contracts and QS parameters are specified. Also, in the OpenFlow model, the single control also has single point of failure issue, and to solve the above issue, we can use distributed controllers in different locations, not only one controller. For example, if we have only one controller and we are using satellite networks, if this controller falls, then the entire communication between the Earth or cellular network which is on the Earth can be set on can be lost can lost the communication with satellite network. The OpenFlow is flow-oriented protocol, as can be concluded also from the name, not packet-based or packet-oriented protocol, and has switches and ports abstraction to control the flow. Also, it has those three parts: channels, flow tables, and group table. in one OpenFlow switch, which is controlled by the OpenFlow protocol from the controller. The controller gives the commands and communicate with the OpenFlow switches. The OpenFlow architecture typically includes those three important components: switches, as we mentioned them, defines an open source protocol to monitor or change the flow tables in different switches and routers. And OpenFlow switches has at least three components: flow tables, as we say, each with an action field associated with each flow entry or each customer, if we have only one customer or end user per flow. A communication channel which provides link to the transmission of commands and packets between a controller and switches. OpenFlow protocol which enable OpenFlow controllers to be able to communicate with any router or switch. Also we have controllers are already mentioned. What is important here that the controller can update, reverse, add or delete flow entries from the flow table on behalf of the user's experiment. Also we have a static and dynamic controllers which enable packets to pass between a group of hosts to travel by putting static or dynamic routes. And the flow entries, each flow entry includes at least a simple action network operation for that flow items. Most OpenFlow switches support those three actions: sending those flow packets to a port, encapsulating these flow packets and sending to a controller, and dropping those flow packets as any other switch or routers, but here we have control from which comes from above from the controller, SDN controller. OpenFlow has gone through many standard iterations, and currently there is version 1.5.1. However, only version 1.0 is available for practical software and hardware design. Version 1.6 has been available since September to 2016, but accessibility only to ONF's members. What is included in the flow tables: classifier, action and statistics. And classifier we have header fields which contain ingress port, Ethernet, VLAN, IP, TCP, UDP parameters like ports, source address, destination address, etc. In the action part we have actions which are mandatory and optional actions, which are going here. Those actions are forward, virtual ports, on which virtual port to be sent, controller, local table, etc. And also you should save some statistics and logs about the flow table. Each OpenFlow table entry has two timers: idle timeout and hard timeouts, which contain the seconds of no matching packets after which the flow is removed, and 0 means never times out or entire will stay. Here we have an example for one table with information about firewalls, flow switches, routers, VLAN switches, etc. and the common action what should be done. Packet flow through the processing pipelines is shown in this slide. So actually the packet, when it's entering in the OpenFlow switch, it goes from table 1, table 0, table 1, etc. up to table n, and after that it executes some action sets and going, and then packets go out. What's happening in each table? For example, table 1. First, he finds highest priority matching flow entry and ingress port, metadata, and other headers. After that, it's applying instructions, which means that modify packets, update matching fields, apply action instruction, update action set, update metadata, and going after that the in the following process, sending mesh data and action set to the next table, etc., etc. Beyond OpenFlow, other SDN protocols also existed. For example, those standards, IEEE uh, 1520 have defined programmable network interfaces, and it can be seen as an initial model of SDN since it also has network programming abstractions. More detail can be found about this protocol here in this paper, and also we have forwarding and control element separation protocol standard defined by IATF given in this paper. Now we will continue with the SDN security, which is very essential part from the SDN. Without SDN security, any communication and any protocols is in vain. Also, we cannot provide satisfying level of quality of service. Because software-defined network can enable the administrators to configure network resources very quickly and to adjust the network-wide traffic flow to meet changing needs dynamically. Security is very crucial here. SDN application, as we says, can be seen as the SDN network brains, since they implement a majority of the network functions, and there should have a high level of security, because each attacks can happen on application layer, control layer, or on data layer. The security is also defined by the ITOT, it is recommendation, and here we have the multi-layer security management, how is going. Again, we have separation of three layers of security, as I said before. SDN application layer security, fulfilled with security management support, case certificate management, data integrity and authentication, etc. On the control layer, we have authentication, authorization, other case certificate management support, and other functionality and processes placed here. And in the resource layer, data layer, we of course have authentication, authorization, data integrity, case certificate management, and all stuffs important for the security. Each of these are defined in more detail in this recommendation. Here briefly we will go through the requirements mapping to secure threats, basically placing tables for the application layer. Those are the security requirements and security threats, how they are mapping those requirements. So for spoofing, repudiation, information disclosure, and etc., we can find those recommendations what to do in situations and threats like this. On the control layer, we have fraud rules, confliction, denial of service attack, spoofing, and many other failure and threats. And in the recommendation, we can find what to do in those situations. Of course, for each layer, we have recommendation and threats. I will not stay longer on those security threats and requirements. and recommendation. You can read more details here in this recommendation given from ITUT. Also, we have many SDN simulators uh, like Pareto optimal controller placement, which is MATLAB based tool, open the lines SDN controller, mini network emulator, and networks simulator 3, which incorporate many models for SDN. All of those are the top popular simulators, which are open and free. Also, we can check if you want to see some of those models for SDN, even in MATLAB. In the beginning, there are we have a demo platform made in MATLAB. Of course, we should have license for MATLAB in order to run this, but there are many other uh, uh, simulators which are open source, like network simulator, mini network emulator, and other which goes without license because they are open free, and open source network emulator given here. So we have many opportunities for simulation, for doing simulation for SDN before implementing something, and this is great for the students and for the researchers. One interesting simulator we can find here in this paper named CloudSim SDN, and it have user content scenario, which is simulated specification, scheduling policy defined on the user interface. Also, if we have workload files and virtual topology configuration, we can directly install here in CloudSim SDN and simulate with this platform. Now we are going on network function virtualization, which is implementing network function in software that run today on properly hardware with high volume standard services and ICT virtualization. What bring NFV is bringing multi-versional and multi-tenancy of network functions, allowing users to use a single physical platform for different application users and platforms, enabling new ways to implement resilience, service assurance, test, diagnosis, virtualization, and security surveillance, and facilitate innovation towards new network functions in the way of network virtualization. This is really emerging technology which going together with the SDN, bringing many challenges and many innovations to a network operators, businesses, regulation, and researchers, performing many high level performance for virtual application and dynamic migration on any platform in an efficient way. What is the difference between SDN and NFV? It's rethinking and relayering. While SDN is typically thought of as managing and automating tasks for physical devices, NFV is all about providing new networking devices, and it is almost always controlled by your virtualization tools. Here we have SDN controllers may or may not be managed by the virtualization tools. Or in other way said, as if we have network virtualization with SDN on network infrastructure here placed in this layer. Now we are going up with NFV, and the virtualization happens very close to application or application layer. Uh, NFV is giving one vision different from the classical network applicants approach. In the classical way of network approach, as we know before, we have messaging routers, different stuffs, fragment and then purpose-built hardware, physically installed per applicants per site, hardware development, large barriers to entry for new vendors, and etc. etc. And we have network horizontalization. And now with NFV, we are moving into competitive, innovative, open ecosystem. Independent software vendors. We have high volume standard services, high volume standard storage, high volume Ethernet switches, because we have virtualization. If we try to define more precisely NFV, what it's transformed how network operators architect the infrastructure by leveraging the full blown virtualization technology to separate software instance from the hardware platform, and by decoupling this function from location from faster network service provision, we can have, for example, one hardware in one country where we are paying lower rent for current and operation, and we can manage it from other location, other country. In this module, we have element management, security, SLB, and other service changing on the application layer from end to end, and other virtualization layers are below. NFV management and orchestration is going first with define services, render service path, and programming service path. This is the circle. What are the benefits of NFV? The benefits are given here: flexibility to easily, rapidly, dynamically provisioning and operating the new services and new hardware and software in various locations, reducing time to market by minimizing the typical network operational cycles of innovation, the CAPEX and OPEX, and more service differentiation and customization. Also, it's improved operational efficiency by taking advantage of the higher uniformity of the physical network platform, and it's homogeneous to the other support platforms. Also, it reduces equipment costs, as said, reduce operational costs, software-oriented innovation, including open source, to rapidly prototype and test new services and guarantee new revenue streams. Also, it is IT-oriented skill set and talents, readily available in a global geographical place, and which are flexible. According to ETSI reference architecture, here we have again this NFV management and orchestration, and one interesting view from ETSI on NFV, which give one interesting approach. Down we have virtual computing, virtual storage, virtual networking, and virtualization layer. Above we have different servicing provided by the VNF infrastructure, and all of them are managed by the NFV orchestration, which is on the top of all, like the main brain of this management and orchestration platform. Above we have many VNF managers controlled by the orchestrator, and virtualized infrastructure manager for different virtualization layers below. Another picture for the architecture of NFV. Above we have abstract network function domain, which including network functions. Below we have NFV service domain for servicing virtualization functions, virtual release, and etc. And below we have network infrastructure, compute and storage, which going in NFV infrastructure domain. So the network is separated on those stratums, different stratums, and the logical model is given here with the virtual network function. So this is how the network architecture for the NFV is shown. The major differences and challenging introduced with NFV are given here. First is the separation of software from hardware, as we say, which enable the software to evolve independently from the hardware, and the hardware to evolve independently from the software, which is very good opportunity and good perspective. Furthermore, we have flexible deployment of the network functions, and if we can automatically deploy network function software on a pool of hardware resources that may run different functions at different times and different data centers. And the third and very important aspect is dynamic servicing provisioning, which means that the network operator can scale the performance dynamically and on a grow as you need basis with fine granularity to control the entire network and to manage the network conditions. What are the relationships between NFV and SDN? We have NFV placed a little above the SDN, which is commonly for automation and control on physical layer, can refer to managing both physical and virtual equipment and environment, but traditionally manage physical network equipment and software. On the other way, we have higher level of virtualization and virtual device provisioning with help of NFV. Again, we have illustration what is the difference between SDN and NFV. If we have one controller looking on a different switches, routers, firewalls, and etc. in SDN, here we have NFV controller, orchestrator, and managers to control different platforms and different infrastructure here, and everything is optional for SDN controller. So that's the high level virtuality. Furthermore, we will present several use cases for NFV. Basically two, not many use cases, in order to have a clear picture about NFV. The virtualization of a mobile core network and a home network. The virtualization of mobile core network, more precisely says APC, target the mobility management entity, home subscriber service, SGNP, PGW, and policy and charging routers functions, which is well known in the mobile and wireless network. The virtualization of a Volt packet core for 4G LTE, LTE Advanced, and LTE Advanced Pro networks, and its coexistence with legacy Volt packet core is done with help of NFV. The coexistence is made possible through technologies such as mobility management entity pooling. You know that it's possible to virtualize only part of the mobile core network, not entire, such as servicing and packaging gateways, and use physical prerequisites for the other components. But however, we can virtualize an entire core network or part of the mobile core network as we want. Virtualization of APC and it coexistence with legacy APC. The legacy APC is organized like this, and with virtualization we have cloud APC. Each of them are have interfaces to the base station. What are the benefits from NFV in Evolved Packet Core? By virtualization, this network is enriched with new functions, can be implemented cloud APC, which allow to move towards a more intelligent, resilient, and scalable core architecture. Each NFV enables flexible distribution of hardware resources to eliminate performance bottlenecks in the network and rapid launch of innovative services, M2M and others. What are the challenges? One of the challenging issue is cloud APC and the carriers that need to dynamically redirect users traffic when the scaling offers services. The second use case for NFV is home network. The architecture virtualization home network is given here. As we see here is the NFV range. This is virtualization of residential gateways as firewall, DHCP service, VPN gateway, and not network address translation routers, where it's kept on NFV. What are the benefits? Reduces the operating expenses by avoiding the constant maintenance and updating the CP customer premise equipment devices and other problems. It improves the quality of experience and quality of service by offering nearly unlimited storage capacity and space, enabling access to all services and sharing many contents. It allows dynamically service quality management and controlling sharing among users, application streams, open APIs, and introduces new services more smoothly and less by minimizing the CPA dependency functions. What are the challenges? Challenges are fundamental issues in this area is the performance virtualization packet processing on the standard high volume services, and to achieve the same or comparable performance in the virtual environment as in bare metal, we need to carefully design the software architecture and configure the system parameters correctly. Finally, the security and privacy issues is very crucial and should be taken common and to minimize the operating cost by affected with those security and privacy, so there is a trade-off. Finally, we have network virtualization, NFV and SDN implemented in the future 5G architecture, which planning to appear in 2020. The first 5G standards, and it's a very hot topic and promising a bright future, this network virtualization. Here is presented the flexibility with NFV SDN. If we have decoupling control from forwarding with SDN, flexibility and forwarding, and flexibility in processing with NFV, with network virtualization, together those are giving more deeper and more higher performances and opening new horizons. For the conclusion, we can say that it is envisioned that network functional virtualization and software-defined network along with cloud computing will become a critical emergency technology in the future, and nowadays it will bring new revolutionized way of organizing the network architecture and monetize their infrastructure and investment. SDN shortly says centralizes and automates management of the network devices, allow the data and control planes to be separated and hence to be easier for improvement and management, parallel to be adjusted, and uh, innovation to flow in control planes and in data planes, and vice versa. And on other side we have network functional virtualization, which is uh, which is bringing unflying revolution among the three, offering more revenue operations in the service value chain, giving more freedom and high level of virtualization. One of the significant caterpillar of 5G undoubtedly are the core network organized with network functional virtualization plus software defined network as the basis for the core and the uh, core part of the network. Uh, in the end, we should present our partners in this uh, project again to emphasize that this presentation and video material is co-founded by the Erasmus Plus program of the European Union, uh, and also this video material is an output of the Erasmus Plus K2 103 strategic partnership for higher education project, named innovative teaching approaches in development of software design, instrumentation and its application in real-time system. uh, I hope that everyone has enjoyed in this presentation, that we have learned a lot of things about network virtualization, about different parts of those two types of software defined network and network functional virtualization, which basically have many in common but also have many different differences, as I mentioned for the end, that SDN is on network layer, uh, more focus on optimization of the physical layer, and network functional virtualization in bringing some application or high level of virtualization. But combination of both of them is the winning combination, which will continue to be hot topic in 5G, and not only in 5G but also in the fixed network, because it is very important part of the core network. That's all. Thank you one more